So I wanted to do another example of calculating the pH of a weak acid titrated with a strong base, where we end up in a situation where we are past the equivalence point. So again, the way we would do this is calculate how many moles of our weak acid we have, in this case formic acid, and how many moles of hydroxide we have added. And if we are past the number of moles of hydroxide added in order to neutralize that weak acid, then we're just going to base our pH on the number of moles of excess hydroxide. So our neutralization we have here is our formic acid is going to be neutralized by the added hydroxide from our, in this case, potassium hydroxide. And that is going to form our conjugate base, which is the formate anion. Not that we really mind, and water, right? So that will be our neutralization reaction. And of course, if we've gone past that equivalence point, we're going to have so much excess hydroxide that any formate anion that's in solution is going to be negligible in terms of aqueous species. So we need to work out if we're before, after, at the equivalence point. So we've got to work out how many moles of formic acid we actually have, how many moles of potassium hydroxide we've added. So we're going to take the concentration, 8400 moles of H2CO2, and I'm going to write that out from molarity into moles per liter just to make the dimensional analysis a little bit easier. So that's moles per liter. The volume that we started with was 157.1 milliliters, which we're going to need to go ahead and convert to liters. 1 milliliter is 10 to the power of minus 3 liters. Let's make that look nice. So milliliters cancels, liters cancels. That gives me my moles of formic acid, and I get 0.131964 moles of my weak acid. So we're going to rinse and repeat that for my moles of hydroxide added. So the concentration, that was 0.86 molarity. So that's moles of hydroxide added per liter. The volume of said hydroxide was 182.2. So I'm eyeballing this in terms of like they are pretty similar concentrations, and we've added more volume of the potassium hydroxide. So I'm guessing this is going to come out as being a little bit after the equivalence point, if my mental math is approximately correct. Let's see. So we are going to convert that into liters. Okay, so how many moles do we end up with? We get 0.15. Whew, okay. 6692 moles of hydroxide being added. So we are past the equivalence point, okay? Or past the equivalence, that kind of looks like. There's not much of a space there. There we go, past the equivalence point. So then what we need to do is we're going to work out our pH based on the hydroxide in excess. So what we need to do is calculate that concentration of hydroxide that we have. So it's going to neutralize the moles of formic acid we have. So we're going to subtract from our total number of moles of hydroxide added, which we've just calculated, the moles of hydronium which need to be neutralized. So that is going to be the same as the moles of formic acid that we just calculated. So that will give us our total excess number of moles of hydroxide, and then we're going to divide that by the initial volume of our solution. And then we're going to add to that the added volume, okay, because the number we're dividing by to get the concentration is going to be bigger, right? If we started with 157.1 milliliters of acid and then we've added 182.2 milliliters of base, we're going to have a larger total volume we're going to be dividing by. So that's 0.156692 minus 0.131. 964, and that will give us mils on the top. Oh, I'm going to have to be careful with this. Am I going to have space? You know what? I'm going to take this down here, so we've definitely got space. Cha-ching. All right, so concentration of hydroxide then is going to be blah, 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 blah. Right, so there's my number of moles on the top, and then the bottom, my volume is going to be 0. Let's just be thorough, 151 milliliters plus the volume added, which was the 182.2 milliliters. So that's moles per milliliter. That won't do. 1 milliliter is 10 to the -3 liters. So I should now get my concentration in moles per liter, and that's going to make everyone happy, right? If those milliliters go away. So I've been a bit naughty with not putting my lines in here, look. Uh, there we go, much prettier. And what does that come out to be? That comes out to be 0.0728695 moles of hydroxide per liter. So that is literally the concentration of hydroxide. We're asked to calculate pH. So just remember, we calculate pH from minus log of the concentration of H plus. So two ways you can do this. We can use Kw to convert concentration of hydroxide to concentration of hydronium, and then calculate pH from minus log of the concentration of hydronium. I like to do it this way to calculate my pOH from minus log of the concentration of hydroxide. Just makes the math a little bit easier. But do be careful here, because when I do this, I'm going to get a number that sounds suspiciously like pH, but it isn't, right? So minus log of the 0.0728795 gives me a pOH value of, it's going to be low, 1.14. Okay, suspiciously sounds like a pH, but it's not. Remind yourself this is the pH of a weak acid titrated by a strong base. A strong base is in excess, so that pH should definitely be a basic pH, because it is basic. It's a basic solution, right? We have just hydroxide in excess. So I've got to remember my pKw expression is the sum of pKa plus pKb, which equals exactly 14. So now I can solve for pKa. That's not what I'm talking about at all. My pKw is this is also true, but not what I need. pH plus pOH. So I want to rearrange and solve for pH. So pH is going to be pKw minus pOH. So don't forget to do that, or you'll be wrong source. Right, so 14.00 minus my 1.14 will give me a pH value of 12.86, which sounds much more reasonable. All right, so hopefully that is helpful. I know these problems take a bit of getting used to, but just remember, you've always got to work out if you are before the equivalence point, at the equivalence point, or after the equivalence point. So the most important thing you do is this first step here, working out the moles of weak acid and the moles of hydroxide you've added, and then you can decide what the strategy you're going to need to use is.